In this video, we're going to be talking about displacement time graphs. Now, displacement time graphs are essentially a way of visualizing how an object moves. So we've got displacement on the vertical axis and we've got time on the horizontal. Now, I've added a few lines to my displacement time graph and I've got three objects here, the red, green and blue, which are going to correspond to these movements here. If I click again, we'll be able to see these move. You can see the blue one's zooming off, the green one's just going off the screen, and the red one's taking a little bit longer going in the opposite direction. You see the blue one, it's covered more displacement, it's got a further distance in that time compared to the other two. And the red one is down here, it's underneath the axes. So what we can learn from this is the steepness or the gradient indicates the velocity of the object. Okay, it's essentially how fast it's going, but it also takes into account the direction of motion. The red one went to the left, so it's underneath. More specifically with the gradient, if we look at the vertical and the horizontal parts of our motion here, on the vertical we get the change of displacement, the horizontal we get the change of time, and if we divide one by the other, we get the change of displacement over the change of time, and that is in fact the formula for velocity. Now, displacement time graphs and distance time graphs are extremely similar to one another, so we can piggy bank a lot of ideas from that other topic from GCSE maths. There are two main differences, and the first is that the object does not have to start at the origin. So you can see here I've got three objects. One of them is starting at the origin, this pink object here, but we've got these two other objects that are 2 and 4 meters away from the origin respectively, and you can see that is indicated by the different heights on our displacement time graph. The second difference is something we've already seen. An object can have a negative velocity, and this looks like the object moving backwards. And when we say that, whenever we're dealing with displacement, we predetermine, we decide in advance which way is positive, and normally that is to the right when we're working with one dimension. So we'll be able to see this move a little bit here. And see that the orange object, even though it started over here with an initial position of 4, it's moved backwards, and we'll see it move again. Fantastic, there we go. Here's some other details that you might use within this topic. If you have a flat horizontal line, it means that there's no velocity, which means your object is not moving whatsoever. This is the blue object here, it's not going to move. This green object has a curved line, and that indicates that the velocity is changing. In this case, the object is getting faster as time goes on, as the line's getting steeper. Here's a numerical example of a displacement time graph. We're going to try and find the following things in green, and there's quite a few of them, but the good news is we can read a lot of them off the graph. Feel free to pause the video at this point and get ready to unpause it whenever you want to look at the answers. Now, the initial and final positions can just be read off the graph. The initial position is where the object starts, which is at 0 meters, and the final position is where the object finishes, which is at minus 10 meters. The total displacement is the difference between where we've started and where we finished, and we've gone backwards 10 meters, so our total displacement is minus 10. The total distance is a little bit more nuanced, as we need to keep in mind that the object's travelled forwards. In this case, it's travelled forward 20 meters, then it's had a rest, hasn't moved, and then it's moved 30 meters backwards from 20 to minus 10. So if we add 20 and 30, we get a distance of 50 meters. Now, the speed and velocity will be similar, except for this last leg, where the speed will be positive, because speed's always positive, and the velocity is going to be negative. This first section here, we've travelled 20 meters in 2 seconds. 20 divided by 2 is 10. This middle section, there's no speed or velocity at all. The object's at rest. And then over here, we've travelled 30 meters in 2 seconds, which is a speed of 15, but it's a velocity of minus 15 because we've gone backwards. The average velocity can be calculated by dividing the total displacement and the total time. So we're going to divide minus 10 by 6 seconds to get an approximate value of minus 1.6. And I think it's 6 recurring actually. The average speed, however, we're going to take the total distance and divide that by the total time, which is going to be 50 over 6 will be something around 8 points. Yeah, we got 8.66.